At this time of the year, families get together to share meals and moments together. It's also the time in the year when it's coldest and we are all susceptible to catching a cold or a flu. There's not much we can do about that now, but researchers at McMaster University in Canada have developed a new cling film-like wrap that can be used to coat objects to make them bacteria repellent, as well as water and dust repellent. They did this through a combination of 3 steps that independently do nothing, but together make a common plastic turned bacteria-proof. The 3 steps involve heating a film of plastic to make it shrink and wrinkle, and then adding nanoparticles to add a tiny roughness to the surface of the plastic. And finally, coating it in chemicals similar to those used on Teflon crockery. Author Tauhid Didar explains.
We took some plastic wrap surfaces that we use on daily applications, for example, polystyrene wraps that is widely used at home for food packaging and so on. And we have created these hierarchical structures on them that completely repels the species around it. It has self-cleaning properties. These species include bacteria, viruses, even droplets of water or other liquids.
And you got inspiration to do this from nature, is that right?
Yes, so we got inspiration from nature, and a very good example of this is the lotus leaf. The surface of the lotus leaf, the structure is very similar to what we have here.
So how were you able to reproduce in the lab what you see in nature?
So adding these hierarchical structures on a flexible wrap wasn't actually that easy. We went through 3 years of trial and error to reach where we are right now. The first step, we learned that we can heat shrink these surfaces to induce the micro wrinkling. We UV treat these surfaces. It makes the wrap surface, it makes it a little bit stiff. And then if you heat shrink that stiff surface, it gives you that microstructures. And heat shrinking is very simple. You can even do it with a hairdryer. And then in a solution, we add these nanoparticles with a certain chemistry to coat on top of those wrinkled surfaces.
How would you explain what these nanoparticles do to the already shrinked wrap?
So they just attach there and provide the hierarchy in the topography. Let me explain it this way. Assume you have a wide land with just hills up and down, and then you have some trees there. Those hills that go up and down, they're like the wrinkled surfaces. The trees that are sticking out in the land are the nanoparticles. So it basically creates that smaller structure on the surface. And that gives the surface that capability to trap air between those tree-like nanoparticles, so that when the droplet of water, the bacteria come in there, they have minimum anchor points to attach to the surface. So that's why they decide not to stay on the surface and move on.
And what's the third step?
The third step is adding a chemistry to the surface, and this is basically fluorine-based chemistry. It's similar to the Teflon-based cookware we have at home, and it's a solution of this molecule called fluorosilane. We dip these surfaces inside, and then it attaches that fluorine groups to it. And the comparison might not be the best, but the fluorine could be the flowers that are coming out of those trees that are the nanoparticles on the hills of microstructures. And that provides an extra step of repellency to the surface.
So why can't bacteria attach to these surfaces?
To be honest, we're still studying this. It's not really clear. We know that they don't. We've done a variety of experiments to show that they're not attaching. We believe that we are minimizing the anchor points. That structure that I explained traps a lot of air onto the surface, and that air prevents the bacteria from liking that surface.
And what does it actually look like? I'm imagining it like a cling film. Is that what it looks like?
It is exactly like the film that we all have at home. Maybe a tiny bit thicker than the wrap that we have, but it's exactly the same.
Okay, and we are able to apply this wrap to any kind of surface in our kitchen and homes?
That's the goal here. We are thinking that we have obviously some high-risk surfaces and high-risk areas. And we think that first we could target those, such as hospital-specific areas in the hospitals or on food packaging or kitchen counters at home, but it could potentially be applied to much wider applications. Now we're dealing with antibiotic-resistant bacteria, and we're trying very hard to discover new antibiotics, new methods to kill these, right? It's all about finding new drugs, but the challenge is that the bacteria evolve and become resistant and more resistant as we move forward. We as engineers, we thought that we can approach it in a different way, and that's to design the surfaces, hoping that this is going to prevent cross-contamination and spread of these superbugs through different settings.
Thanks to Tauid Dider from McMaster University in Canada, explaining his work recently published in ACS Nano.